Mechanical Power Transmission, Part 2 of 2. Motion reversal and idler gears. One other aspect of gear designers must consider is how they reverse motion. The driver gear spins in the opposite direction of the driving gear. To make the output gear spin in the same direction, some designers will use what is called an idler gear. The idler gear has no effect on the overall reduction. One can similarly calculate the gear reduction of the idler gear sets in two stages. Gear reduction 1, 36 to 36 to 12. You can see the 36 here and then the 12 here. Gear reduction number 2, 60 to 36. You see here 60, 36. Overall gear reduction 1 times gear reduction 2 equals 3 times 1.667 equals 5. The only gears that matter to reduction are the first gear and the last gear. Idler gears can be very useful, especially for spanning long distances. Compound gear reduction. A design may require more mechanical advantage than a single gear ratio can provide, or is otherwise impractical. In this situation, a designer can use multiple gear reductions in the same mechanism. This is called a compound gear reduction. Compound gear reduction. In a compound gear system, there are multiple gear pairs. The resulting compound gear system still has a driving gear and a driven gear, and still has a gear reduction. The compound gear ratio is calculated by multiplying the gear reductions of each of the individual gear pairs. So you can see compound gear reduction, reduction 1 times reduction 2, 60 divided by 12, again 60 divided by 12 equals 5 times 5 equals 25. If we look back here, here's 12 here, so 12 and 60, and then another 12 and 60. And those two groups multiplied together give us our 25. Other types of reduction. Gears aren't the only mechanisms in robotics that provide gear reduction. The same principles apply to sprockets and chains and pulleys and belts. You can see our 25 millimeter diameter pulley. Here we have a 45 millimeter. So the ratio is 25 to 45. And then the reduction 45 divided by 25 equals 1.8. Other types of reductions. Pulleys and belts don't have teeth, but their ratio can be calculated by comparing their diameters. Both of these mechanisms provide more options to designers working with mechanical power transmission. Sprockets and pulleys work great in situations where torque needs to be transferred over long distances. Unlike gears, these systems don't reverse the direction of motion. Applying gear ratios to DC motors. Adjustments to mechanical advantage are important to the design of DC motor systems. The first step in these types of design problems is to calculate the load the motor must be under to meet the design criteria and the formulas. After that, it's a matter of taking the output requirements and input limits and calculating the ratio required. So here we go. We have our information of our VEX 2-wire motor. The first step is to calculate the torque applied by the arm. Torque equals force times distance, so we have 30 newtons times 0.5 meters, which gives us 15 newton meters. For the configuration of an arm, assume the system has one VEX 2-wire motor 393 and that this motor cannot draw more than 2.5 amps at any time. What gear ratio is needed to lift a 30 newton object and not exceed the current draw? So that's where we get our 30 newtons there. Okay. The next step is to calculate the torque load, which will cause the motor to exceed 2.5 amps. So our torque load equals our given motor current minus free current times the stall torque divided by the stall current minus free current. So our given motor current is 2.5 amps. Our free current is 0.37 amps, okay, times 1.67 newton meters. That's our stall torque. Get that from right there. Divided by our stall current, 4.8 amps, minus our free current, 0.37 amps. See how we go through the calculations here to come out with a torque load of 0.803 newton meters. So if the normal torque load on the output of the gearbox is 15 newton meters, and the load on the motor can't be more than 0.803 newton meters, what gear reduction is required? So the output torque equals the input torque times the gear reduction, We rearrange our formula to get our gear reduction equals the output torque divided by input torque. So we get 15 divided by 0.803, and our gear reduction comes out to be 18.68. Based on the example, the gear reduction required is 18.68. It is not always possible to achieve specific gear ratios with the gears on hand. Assuming the designer only has 12-tooth, 36-tooth, and 84-tooth gears, calculate a compound reduction that creates the overall gear ratio required that results in a reduction more than 18.68. So here we have a bunch of all of our different options here. One can look at the big list of reduction options and see which ones multiply together as a compound reduction comes close to 18.68. Okay. You can see here we have a 36 divided by 12 gives us 3. So we have all of our different options, and we're going to look for one that comes close to 18.68. Um, 12 to 60, and then another 12 to 60 gives us 25. 25 is greater than 18.68, so it's acceptable. However, 25 is a lot more reduction than required, so the arm will move slower than is necessary to achieve the design goal. Is there another option which is closer to 18.68? We go 12 to 36 and 12 to 84 gives us 21. You can see how 36 divided by 12 gives us 3, 84 divided by 12 gives us 7, 3 times 7 equals 21. 21 is greater than the 18.68, so 12 to 36 and 12 to 84 is an acceptable choice. Arm design. Designers should create a single motor, gearbox, and arm system that can lift the weight of a single game object. Designers must choose an arm length appropriate for the game, which fits within the 18-inch robot size requirement. The gear ratio should be calculated so that the motor can be loaded such that it draws no more than 1 amp of current. Conclusion. Mechanical power transmission systems are very important in the design and construction of competition robots. A designer's ability to vary the gear ratio and the mechanical advantage in a system gives them the versatility necessary to accomplish whatever work needs to be done with whatever motors they have at the expense of speed. At the simplest level, designers just need to determine their inputs and outputs, calculate the difference between them, and set their gear ratio accordingly. Modeling and articulating Scoop. Go to this link and watch the videos overview, videos 1 through 5, and the summary, and then come back and finish this video. The link will be in the description. Formulas. Gear ratio equals driving gear teeth to driven gear teeth. Gear reduction equals driven gear teeth divided by driving gear teeth. Output torque equals input torque times gear reduction. Gear reduction required equals output torque divided by input torque. Output speed equals input speed divided by gear reduction. Gear reduction required equals input speed divided by output speed. Compound gear reduction equals gear reduction 1 times gear reduction 2 times gear reduction 3 times all other gear reductions. Answer the following in your engineering notebook. How do the different types of gears provide an advantage in your arm design? And how do the mathematical calculations help you to determine what type of gear ratio is needed in your design?